Greetings from the Department of ECE. I am Anita, working as an Associate Professor in the Department of ECE. So here we are going to learn about Module 3, which is ARM Embedded Systems under CO and ARM Microcontroller subject with the subject code as 21EC52. These are the contents which we are going to cover under the VTU syllabus in Module 3. So first we will be talking about ARM Embedded Systems, risk design philosophy, ARM design philosophy, and the embedded system hardware, followed by the software. Then in the second part we'll be discussing about ARM processor fundamentals, core data flow model, registers, general purpose registers, CPSR registers, then some of the pipelining concepts along with exceptions and interrupt vector table, followed by the core extensions. This is a textbook which you are supposed to refer. ARM System Developers Guide by Andrew and Sloss. These are the contents which I am going to cover in this topic, which is about risk design philosophy, ARM design philosophy, and embedded system hardware and software. So coming to ARM, as we all know that ARM is nothing but advanced RISC machine. So it uses a RISC architecture, which is nothing but reduced instruction set architecture. Reduces the instruction set, means in ARM is a RISC design, uses a RISC design philosophy and delivers simple and powerful instructions which can be executed within a single cycle at a high clock rate. So with this powerful instruction and completing in one clock cycle reduces the complexity of the instructions performed by the hardware. So meaning it is easier to provide greater flexibility and intelligence in software rather than in hardware. That means complexity is with respect to the hardware rather than software. So it places a greater demand on the compiler. So you can observe the difference between RISC and CISC design philosophies. So in CISC architecture you will have a compiler and processor. Even in RISC you have a compiler and a processor. So in RISC architecture more emphasis or more complexities with respect to the compiler, less is with respect to the processor, whereas in CISC processor will be having a greater complexity compared to the compiler. So CISC indicating about a complex instruction set computer, it relies more on hardware for instruction functionality and reduces and instructions are more complicated compared to RISC type. So this is a tabular column which is giving a major differences between RISC and CISC. So CISC, as I told it, takes multiple clock cycles to complete the instruction, whereas RISC uses a simple instruction and can be completed within a single clock cycle. Emphasis will be more given on hardware in case of CISC type, whereas in software in case of RISC type. So you will have a complex instructions which are executed by the microprogram or a processor, whereas here it is executed by the reduced instructions you have and is executed by the hardware. So here in CISC you have a variable format instruction, a single register set and many instructions that you have, whereas in RISC type you have a fixed format instructions, multiple register sets that will make use. So in RISC type many instructions that you have and you have many addressing modes, whereas in RISC type you have fixed instructions and only few addressing modes. In RISC conditional jump is based on a bit anywhere in the memory, whereas in CISC it is based on the status register bit. Memory interface is embedded in case of many instructions in case of CISC, whereas memory reference in embedded system is with respect to load and store instructions. Or you can say that RISC architecture is load and store architecture. So coming to the next topic, which is risk design rules. So majorly focusing on the instruction set, pipelining technique in risk type, and registers which it supports, and the load store architecture. Coming to the instructions, as it is a risk type, already told, reduced number of instructions. You have simple operations that can be performed, and most of the instruction which will be completed within a single clock cycle. Compiler or programmer synthesis, which is complicating the operations. So whereas in CISC type, the instructions are of variable size and take many cycles to execute. Coming to the pipelining, the process of means in pipelining, 3-stage pipeline or 5-stage pipeline or 7-stage pipeline techniques you have. So pipelining basically it means processing of the instructions. They'll break down into smaller units. That smaller units will be performed in clock cycle. Instructions are executed in parallel by the pipelining technique. Like you have a decode, execute. It is a two means fetching, decoding, and executing, 3-stage pipeline. In one clock cycle, if it is decoding, in the second clock cycle, first instruction will go for execution, second instruction will be decoding. Likewise, pipelining will be used in a case of supports in case of risk type. Pipeline usually it advances one step in one clock each cycle for maximum throughput. Whereas in no need for an instruction to be executed by mini program called microprogram as on a CISC processor. Coming to the registers, you have a large general purpose register set in case of RISC type. Whereas CISC type, you have a dedicated registers for specific purpose. Here, any register can contain either a data or an address of the memory. Registers mainly meant for accessing a local memory, means fast accessing of the local memory storage in case of all data processing instructions. So coming to load store architecture in case of RISC. So the processor operates based on load store architecture. So indicating usually the processors operate on the data which is held in the registers. Sometimes if I want to load the data or store the data with respect to the external memory, then it can be performed between the memory and the registers using a load store instructions. So loading in the load the data from the register from the memory to the register, whereas store indicating storing the data from register to the memory. So in CISC, data processing operations can act on the memory directly, whereas we don't have load and store instructions separately. So comparison with respect to RISC and CISC, if you observe, RISC architecture which supports all these four design rules. It supports many reduced number of instructions. Pipelining it supports. With pipelining it increases the throughput. Many general purpose registers that it supports, and accessing the external memory is through load store architecture. So with this we can conclude that traditional CISC processors are more complex and operate at lower clock frequencies, whereas RISC is the one which operates at higher clock frequencies and it is a simple one. So the design rules are simple one with a RISC processor. So ARM processor which implements using RISC type. Coming to the ARM design philosophy, the physical features that have driven the ARM processor design are mainly you have a portable embedded systems. Usually they require battery power. The ARM processor, whatever you make use to design means in a small system, we expect the reduced power consumption and the extended battery operation. So majority of the applications like PDAs, mobile phones, they use a small portable embedded systems within that ARM is a processor which is preferable. The reason that we'll see, we'll have a high code density. Means if I choose ARM embedded systems, I need to have high code density because embedded systems have a limited memory. So with respect to the cost and the physical size restrictions, one has to have operate that applications with a limited onboard memory. Embedded systems are price sensitive, so indicating about they are slow. They use a slow and low cost memory devices. With that, we can support for high volume applications like digital cameras, and they reduce the area of the die taken up by the processor, taken up by the embedded processors. To reduce the cost of the design and manufacturing for the end product, we do prefer embedded systems with a price sensitive. ARM has incorporated hardware debug technology, and ARM core is not a pure RISC architecture. It implements both because of the constraints of prime applications, that is embedded system applications. ARM is not a pure RISC type of architecture. Coming to the instruction set which is used for the embedded systems. So the ARM instruction set differs from pure RISC definition in several ways that make the ARM instruction set suitable for embedded applications. So the major differences are variable execution cycle execution and inline barrier shifter, thumb 16-bit instruction set, conditional execution, and enhanced instructions that you have in ARM RISC architecture. So first one indicating about variable cycle execution for certain instructions. So not every ARM instruction executes in a single clock cycle. For example, like a load, store, multiple they use a variable number of instructions. Execution cycle is not a single cycle. It takes multiple cycles to complete. The transfer can occur on a sequential memory basis. Coming to inline barrel shifter, you have a inline barrel shifter which is supported as a hardware component along with the ALU, which expands the capability of many instructions. It is majorly incorporated to improve the core performance and the code density. So purpose of barrel shifter is many of the operations like multiplication, division, those operations that you can perform through barrel shifter. Coming to 16-bit thumb instruction set, ARM also supports along with 32-bit instruction set, it supports 16-bit also. Major purpose of supporting a thumb instruction set is to improve the code density by about 30% over 32-bit fixed length instructions. Then conditional execution, almost all instructions in ARM processor are of conditional execution. So that means if that condition is satisfied, then only it performs the next instruction. The major purpose of this is to improve the performance and code density by reducing the branch instructions. Next you have is enhanced instructions. Along with these type, ARM processor, it supports DSP instructions also to support for higher bit multiplication and faster performance of ARM processor. These additional features has made the ARM processor as one of the most commonly used 32-bit processor in most of the embedded system applications. Thank you. Next class we'll see about embedded system hardware, then followed by software and core data flow model. Thank you.